Okay, we are recording. Let me pin my video. So that's what it records. Okay, I'm going to switch to the document camera. Okay, so today's agenda. So we're kind of doing what is this? There. An Ohm's Law intro. So housekeeping. So I sent y'all the Bad Movie presentations, and yeah, honestly, I'm just super duper proud of y'all. Like all the presentations are really darn good. And it makes me really happy to see like how much you've learned in this class. Okay, for a warm up, we're going to go over some of the tougher stuff on homework. And then today's lesson, we're going to go kind of into Ohm's Law. And I was going to give y'all homework, but luckily for y'all, I didn't finish it yet. So while I would really, like, if we were in class, like in school, I would have y'all be working with like breadboards and stuff to, you know, to like practice and like make little circuits. But unfortunately, you know, state of the world, the next best thing is that I found a really good online lab where you can still like build circuits. So I'm not going to assign that for homework. Like you're not going to have homework over the weekend, okay? But it is going to come next week. So today, just hold on. We're going to go over some more cool circuit stuff. So first, I want to go over, here we go. So I'm also going to link this as a PDF in the chat in case it's hard for you to see the document camera. So I'm not going to step away this time for y'all to talk about stuff. Also, I feel like y'all are very tired and sleepy this morning, which is fair. So we're just going to talk about this together. But I do ask that we actually do talk about it, okay? So I am asking that you unmute your mic, that you like engage. Okay, so number one, in the following scenarios, the light bulb doesn't light up. Why?
I said it was a complete circuit.
I like that. I like the not a complete circuit. Why is it not a complete circuit? Ooh.
There's no current.
Because the wire is not touching the.
Yeah, I gotcha. Okay, y'all. I don't want to be that teacher, but I'm gonna like do executive move and like unmute all your mics so that we can actually like all talk, so it's not the same two people, which I do appreciate y'all. But so please, come on. I know it's a Friday, but hang in there. You're completely right. This doesn't actually make a complete circuit. So we had talked about in a lot of detail the idea of that river current, right? So we've got to have some current, we've got to have some flow, we have to have some difference from start to end for the electrons to flow. In these examples right here, these are examples of like a stagnant pond. There's no current flowing, you know, it's not going to light the light bulb up. And then I asked y'all to like draw out like what would light it up. And the homeworks that I did check so far, they're all great. You're completely right. You've got to connect the positive and the negative to the light bulb. Okay, number two is actually pretty hard. And if you weren't exactly sure, that's totally fine. This was a hard one. So explain how electronics can begin operating almost immediately after you flip a switch, even though individual electrons may take hours to reach the device. So you're in your room. That's your room. Switch. You flip the light switch, and your light bulb in your room comes on almost instantly. But when you think about it, the little electron that started over by the switch, it doesn't travel to the light instantaneously. So how is it that the light bulb can turn on like almost instantly? Anyone have ideas? Carter, raise your hand. Yeah. And Charlotte, whatever. Y'all can just whatever talk. It's cool.
I was
I'm not sure, but I guess that maybe the sheer number of electrons kind of push each other to the lights, like to the light, since they're going from the positive to the negative. Or sorry, from the negative to the positive, and they want to get to the positive, but they have to go past the light bulb. Maybe the sheer number just kind of pushes each other to be the first to get to the positive end.
So Carter, you said you're unsure about that, but you're totally completely right. So I'm really glad that you shared that, even though you felt a little unsure. Totally right. So if we imagine that wire, and so I've chopped through the wire so we can see into it. You're totally right. There are electrons. I need blue for electrons. There are electrons everywhere in that wire. So as soon as you flip that switch, that sheer like force, I kind of think of it like a tidal wave almost, like all of them push at once. And so even if you flip the switch over here, the electrons over here are also being pushed. Totally on the money, perfect. Okay, last question. So I wanted to revisit the birds on the power line. I'm gonna draw a little picture. So a bird is just on the power line. Why doesn't it get electrocuted? And in what scenario would it actually get electrocuted? Laura, yeah, it's your hand.
I said that the electrons, like, they weren't attracted to the bird, and they were more attracted to, like, the keep going down the wire to a positive source. But if the bird had like was like a positively charged thing, then they would be attracted to it.
So I do agree with you in that if the bird were overall positively charged, like they would be attracted, but the birds are generally overall neutral. They're like us, right? Like it's not like when they touch each other, they they just like static electrocute each other all the time. But I like the path, like the logic you're on. You're saying, again, there has to be some voltage difference. There has to be some plus side and some minus side for the electrons to flow. So you can kind of think of the bird just on the power line, again, like that example of the stagnant pond. When its feet touch, little feet, when its feet touch the power line, there's no difference. There's no like positive or negative end of the bird. But when that bird touches the ground, y'all, I actually had a dream the other night that one of these birds existed with these really scary long legs. It was a terrifying dream. But if the bird touches the ground, you can imagine that all these electrons in the power line, there's now a flow of charge from one end to the other, from the power line to the ground. So once the bird basically makes a complete circuit, once it connects to the ground, then it turns into a crispy chicken nugget. And these same ideas are actually like, I hope y'all have never had to actually like jumpstart a car. But if you have, like, these same principles apply. Like you have to connect the clips to like a specific terminal of the battery, to, you know, a ground, to, you know, it's all these principles. It's just in the scenario of your car. So yeah, I guess what I'm trying to say is be careful if you're working with like heavy duty batteries that you don't get fried. Questions, concerns, comments? Okay. And also, y'all, I really do appreciate that you're like interacting. Again, I know it's a Friday morning. I do appreciate it though. Okay, I want to jump into some fun circuit stuff. So, whenever I try to get paper, like during class, like just a sheet of paper, it never comes off. Like, but then when I'm not in class, whatever. The Zoom overlords are making teaching difficult. Okay. So last time on Tuesday, Wednesday, whenever I last saw you, we looked at how to build a very simple circuit. And I want to start talking about how we scale up from it, how we go from just lighting up a light bulb to, you know, the actual circuitry, you know, that's in electronics in your house, all that good stuff. So let me switch back to the webcam or document camera. So today what we're going to go over is Intro to Ohm's Law. Oh, sorry. There we go. And originally I was going to make this lesson like concept plus numbers, but to be honest, I think it makes more sense to do the concepts kind of first, so we can tackle the numbers later. Okay. Last class, we went over a simple circuit consisting of a power source, like a battery, a lamp, and then we also talked about the idea of a switch. But in like real life electronics, the circuits are a lot more intricate. And I'm not expecting y'all to draw these down, okay? Write these down. But I just want to show examples. So I actually pulled these off of website. I forget exactly which electronics these are for, but you get the point. This stuff is complicated. And so, you know, each shape, each symbol represents a specific type of you know, component in the circuit. And I hope you can kind of see there are some patterns that you can pick out from these schematics. And what I want to stress is that it's not like, you know, electricians or electrical engineers. It's not like they just like roll the dice and are like, oh, yes, let's connect this to that to that. Everything has a purpose, everything has a reason, and we are going to start getting into how we figure out what should go where. So I want to show another example. This is another circuit. And again, to me, they're kind of like, they're like an electrician's version of Sudoku. Again, there's a reason why we put everything where we put it. But to really get into this, I need to introduce another concept to you. So we've talked about voltage, we've talked about current. Now let's introduce another idea. And to introduce that, I want to link it back to something we've already talked about. So when we've talked about stuff like work and energy and, you know, like doing macroscopic motion, we've thought about the idea of friction. Sometimes we simplify it and say, we're ignoring friction. Sometimes we can't ignore it. But I just want us to think about the concept of what friction represents, right? So you all know my favorite example of me pushing my dog in a box, right? Wow, that's whatever. Oh God, that's a bad dog. Y'all get it. So I have some F push, so some force pushing this object along. But then, I did not leave myself enough room. Dark here. Y'all know that if we take it into account, a lot of the times we have a force of friction as well, like maybe, the carpet or, going uphill. So we have some motion being opposed in the opposite direction. Let's apply this to a circuit. And where can we apply it? I want us to think about a wire, a metal wire. So it's a conductor, the electrons flow through it. You can imagine that the current is basically like the force of the electrons, right? So it's going in a certain direction. But as Carter said, think about like the sheer number of electrons in this wire. So I'm going to represent that as like a squiggly line. Lots of electrons. Imagine like these electrons are in a mosh pit for a concert. They're not going very far until they bump into someone else, right? So another electron or the wire. So there's this internal force, this kind of electron friction almost. But I'm not going to call it friction. So it's kind of electron friction, right? I'm not going to call it friction. The official term for it is resistance. So, dealing with electronics, we are thinking of three major concepts that all work together. That is voltage, current, and resistance. Resistance. So these three main ideas are what we're going to look at for how to design our circuits. And last time, we looked at a very simple circuit. So that circuit consisted of a wire to connect everything together so the electrons can flow, a battery, and a light bulb. So I want to take this idea of resistance and think in terms of this circuit. So I'm going to draw it again. We've got our positive terminal, we've got our light, we've got our battery. So again, just big components, simple system. You know how in a lot of like previous units and stuff, when we talk about like air resistance or friction, we kind of said like, oh, let's just forget about it for right now. Let's just simplify it. We're kind of going to take that approach for our circuits right now, okay? Because when you start considering that, that's just way beyond the scope of what we need to be talking about, okay? So in this little circuit, we have this wire, which I'm just going to highlight. Okay, so I am going to say that this wire is ideal, meaning that the wire has no, resistance. So you might be wondering at this point, okay, so if we're like assuming a wire is ideal, why do we even care about resistance? For that we kind of have to start talking about Ohm's law. And Ohm's law combines all three of these ideas. So let's say I want to light up this LED in my circuit. Y'all have probably experienced, like, at some point, like, oh no, like, you used too strong of a battery and the light bulb burned out. Or what was the other example I thought of? Well, you get the idea, right? So like this LED, we need a certain amount of energy going to it, and we don't want to overload it, or we could fry our LED. So when we think of how to design our circuit so that this LED lights up without toasting itself, this is where the idea of Ohm's law comes in. So in Ohm's law, we relate those three ideas together: voltage, current, and resistance. And we find that actually voltage is equal to current times resistance. What do I actually mean by resistance? Like how does that come into play in making a circuit? We've talked about before that the current in amps, that's the flow of the electrons. The voltage is how hard you push the circuit juice, the current. And the resistance is like the friction opposing the current. It's like trying to push box uphill. Or the other. I like this little cartoon. It's like the current is trying to go through the wire, and our power, our voltage, is trying to push it through. But we can increase or decrease the resistance to slow or speed up that flow. And this relationship between these three helps you figure out how to power your light bulb without it burning out. Too much current, it might burn out. Too much voltage, pushing it might burn it out. So maybe you need to change the resistance to actually like slow that flow again so your light bulb doesn't explode. So, Ohm's law. Voltage equals current times resistance. If you end up going into like the electrical engineering or electrician kind of field, this is going to be like your holy equation. This is so super duper important. And I'm gonna write this out in terms of the variables, okay? So voltage is V, current is I, resistance is R. V equals I, R. This is Ohm's law. In a second, we're gonna again look at this in terms of like a circuit. And next time we're gonna look at more of like calculations, okay? But y'all know that I'm big on units. Units, so let's talk about units. Voltage. Well, you know that's in volts. V. Haha, look there. Same variables, very useful. As opposed to all the other redundant variables. Current is measured in amps, or A, and resistance. So the guy that really helped pioneer this, his last name was Ohm, or I forget if it has the S in it, whatever. He was Ohms, right? Person was Ohms. So when they were deciding on the units, they were like, okay, ohms sounds like omega. So let's make the unit for resistance the ohm after the dude. And then the symbol, the variable, is the Greek omega. So this little funny horseshoe. I wish that these people who are deciding on the variables could make it a little less, less like just. Anywho, you get the point. VA omega. Okay, these are our units. Okay. Question at this point. Cool. Okay. Now. Okay. So at this point, again, you might be like, okay, Ms. Duckworth just told us we're going to assume the wires are ideal. So, like, how do we introduce resistance into our system? We do that with, where did my individual one go? I showed y'all last time some parts. So this is a string of resistors. Let me actually pop them out. I keep losing the ones I'm popping out. Husbands and ladies. So this, let me see if it can focus on it. Nice, good job, document camera. This is a resistor. We are not going to go into the material properties of what makes a resistor a resistor. If you're curious, shoot me an email later. For right now, all you need to know is that we have specific components to increase the resistance in the system. So this can help slow down that flow of electrons. And so you can buy these in giant packs with, 2 wired connections so you can connect to your circuit. And you'll see that there are actually these colored bands. And those actually correspond to what resistance, like how many ohms this resistor has. Where's this? There's actually a standardized system for this. So refocus. Wow, that didn't work. Come on, document camera, don't do this. There we go. So you can see that there are different colored bands, and they correspond to different like resistance values. So in that really complex looking, in this really complex looking circuit, we can have like various types of resistors in here. Okay, so I've shown you the actual component we use. Isn't this cool, y'all? Like, we people make these things, and then we use them to do technology. That's really cool. Okay. So we use resistors to introduce resistance. For once, thanks to people who developed this, that they use words that make sense to pair together. Okay, how do we actually draw this number circuit though? So let's consider our simple circuit again, in which we have wire to connect everything. And again, we are considering this wire for right now to be ideal. We also have resistors we can add in. And then let's have an energy source, a battery. And let's have a light bulb that we're trying to light up. So let's draw this. We've got the positive terminal of the battery. We've got my light bulb. And let's say that this light bulb, we want to reduce the current going to it so that it doesn't explode, it doesn't burn out. So I'm going to introduce in a resistor. Just like other components of the circuit, we have a specific symbol we use for resistors. And that symbol is a harsh squiggle. So there's not a certain number of squiggles you're supposed to use in it. Most of the time people use about 3. Don't use like 8, don't use 10, that's like way too much. Just make like a 3-turn squiggle. And this is a resistor. This is the symbol. Questions about this so far? Okay. But again, let's look back at one of those complicated circuits. So here's my nice little simple one. Let's look back again at this one. Okay. So you can see in certain places, like, focus. Yes, good focus. You can actually go and see like, oh, resistor, 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 resistor. Like they're all over. And we'll get into some of the other components later on. But these are placed in specific strategic positions so that your circuit will work. Again, it's not like these people are just like rolling dice and they're like, oh yeah, let's stick resistor 1 here. And let's start talking about the patterns of how to set these up. So you notice that for circuits, we use like basically like rectangular kind of like patterns, right? Like you normally, like the circuit itself with the wire is not like a circle or, you know, a triangle. We have the wire in kind of these like rectangular or like linear patterns. So how do we figure out what pattern we need to use? To get into that, I want us to think of an analogy first, because I think this analogy will help make sense of the circuit. Let's consider that our wire in our circuit is like a highway. Maybe it's a single lane highway, maybe it's multiple lanes of highway. How do the number of lanes in our highway and the positioning affect the voltage, the current, and the resistance? Remember those big 3 IDs in Ohm's law. Let's say we are looking at our simple circuit where we just introduced 1 resistor into it. So that example was like, like this, right? How many different ways can you arrange this resistor in a single lane on a highway? That's what this first scenario represents. So you can imagine this car, this resistor, is scooting along. It's in its lane, it does its thing, it has a certain current and voltage associated with it, right? Well, let's start putting more components in. Let's consider that we have 3 resistors. Well, let's say that highway is a single lane highway. So those 3 resistors can only be placed one after the other. They can't jump in line. They can't, pass another car. They are just one after the other ducks in a row. We'll do some number calculations next time, but just consider how this kind of bottleneck might affect the current or the voltage, right? So imagine it's like you've got a lot of traffic and you only can go in one lane. Or maybe that highway opens up and there's 3 lanes across. All 3 electrons can go at the same time just in different parallel paths. Again, just consider in your mind how this might affect the current and the voltage. Would it ease it up? Would it bottleneck it? What do you think would happen? So if you notice on this page, it says 3 resistors placed in series, or 3 resistors placed in parallel. These are the 2 main ways you can organize parts of your circuit. So let's take this idea and apply it to drawing a circuit. Questions, concerns, complaints up to this point? Okay, so how do we position our stuff? I'm just going to say stuff for all of our components in our circuits. The examples I'm going to draw, there we go. And the examples I'm going to draw, I'm going to say that I have a battery and 2 resistors. So I'm not actually powering anything in this circuit. I'm just trying to show y'all how they can be arranged, okay? We'll get more complicated later. Okay. So in the car example, we saw that we can have in series or in parallel. There we go. So let's draw both scenarios, how to draw those. So I have a battery. There we go. Let me first draw the one in series. So again, series means one right after the other, ducks in a row. I'm going to draw my battery. And I'm going to draw 1 resistor here. And 1 resistor here. If you were to take the wires connected to the battery and pull them apart so that you have basically just a flat wire, this resistor, I'm going to say R1 and R2 are one right after the other sequential if you pull it apart and hold it so it's just one linear wire. This is in series. I do want to draw another way to represent this. So at first you need to be like, oh, that's not series because they're on different sides of the wire. But again, imagine unraveling this, they'd still be next to each other. Drawn another way that is the complete same, it means the exact same thing, is this. I have my positive terminal with battery. They're just now on the same side. Again, these 2 scenarios are completely equivalent. Questions up to this point? A lot of this is getting used to the visual of what a circuit looks like. Okay, parallel. Oh, these, I'm so bad at drawing these because I'm not good at drawing parallel stuff. Okay, as the name implied, and also from the highway example, we're going to have literally parallel lanes that our resistors are going to go in. I'm just going to rotate it. So instead of it looking like this, 3 lanes this way, I'm going to rotate it this way. So they're parallel with the horizontal. Again, I'm going to draw the battery. Okay. 2 resistors in parallel. Draw the first one. Second one. Second one cannot be, again, if you unravel this wire, it cannot be ducks in a row. So how do you introduce that? You are literally going to draw them parallel to each other, literally like parallel lines. So R1, R2. I think the parallel scenarios are super more difficult to visualize than the series. And if we go back to that complicated looking example, if you actually start looking at this, you'll start to see, oh, these are in parallel, oh, these are in series. And what you'll notice is that we can have a hybrid mashup. Like, circuits are not just all in series or all in parallel. You utilize them based on what you need. Because the properties of voltage, current, and resistance. So again, Ohm's law, right? Ohm's law. These values change, like they are physically influenced by how you create your circuit. And we're going to get into the math of how that happens next time. But I just want you to start thinking that, okay, yes, there's a reason why we would use series. There's a reason why we would use parallel. And I actually want to go over. There we go. Okay. Questions, concerns. I just want to go over one last example, and then we'll call it a morning. Okay. I'm going to draw a circuit. So I don't want us to just like dive into this one. This one's really hard. So let's start building up, okay? So let's say in this example, I have ooh, wow. Trying sideways is hard. Okay. Let me label what we have. So we have battery, and see how this time for the battery, it's on like the vertical side. A lot of these circuits, you may have to like actually like print it out and kind of like move it if it helps you visualize it better. So we have battery, we have resistor 1, resistor 2, resistor 3, and a light bulb. So see how like we have like, it's not just one cut clean kind of design. We can integrate and combine ideas together. So resistor 1 and resistor 2. Series or parallel? Are they in series or parallel? How about series, thumbs up?
Series.
Nice, thank you. Okay. Series. Boom, perfect. They're one right after the other sequential. What about the battery and R2, resistor 2? How about this? For these, can y'all give me a thumbs up for series and a thumbs down for parallel? So, battery and R2. Series or parallel? Nice, nice. Okay. I see a lot of series. You're completely right. Again, imagine if you were an electron, you're like in a little car, and you travel along, travel along, travel along. You're in the same lane the entire time. So you're in series. Okay, so,
Miss Duckworth,
yeah.
why do you might have said this already, but why do you want to add in resistance?
So, let me switch to my face so I can. When we think of, hold tight. Let me actually grab one of the things I showed last time. I have to go grab it from an office. Okay, let me. So the short answer is that certain electronic components require certain parameters, certain voltages, certain currents, and if you undershoot or overshoot, it won't work. So, so again, it's so spiky. So again, this motherboard. There are tons of resistors in here because maybe as the energy flows from the CPU to a graphics card, maybe the current needs to change for that graphics card to work properly. So inside the circuit, we introduce, it's kind of like stuff that like modulates your inputs. Yeah, so it's like all the stuff in this on this motherboard, it's not like they all work just with the same current or just with the same voltage. I hope that helps. So it's kind of like, again, oh god, it's kind of like a Sudoku puzzle. Like you've got to put the right pieces to make everything fit. And again, like y'all are going to start, like when I have y'all do that like online lab and stuff, like I hope it becomes more clear of like, yeah. Okay. So heavy. Okay. I want to ask y'all one last question about this little practice circuit. Okay. So then, light and R3, series or parallel? Thumbs up, thumbs down. Thumbs up, series, thumbs down, parallel. Awesome, y'all are doing so great. Perfect, this is parallel. So I'm gonna try to train your brain so you can look at this and be like, ah, yes, this is parallel or this is series. So then when you look at something like this, you can start recognizing the patterns. Because for this, you might be like, oh no, this is a lot of stuff going on. But we're gonna build up. Okay. Okay, questions, concerns, anything else? I know this was a lot of new content today, y'all. Yeah. Okay. Also, y'all, I'm so upset. So in eBlock yesterday, when I was going through the problems, I was wearing long sleeves, so I used my little baby hands to like go through them, and no one said a word. I was so upset. Okay. Well, wait. One last question before we go. Did y'all want me to do another Jackbox game night? I had a couple people say sure, but do you want me to do it like, I don't mind, I can do it like today or tomorrow, whatever, if you wanna. Just cause, yeah, I know, we're kind of winding down school, so. No comment, good, okay. Okay, well, I'll send out an email if I end up doing it. What else? I hope y'all are doing okay. It's so nice to see all of you, thank you. Okay, as always, if you have questions, feel free, shoot me an email, okay? Hope you have a good rest of the day.
Bye.
Bye.